So what's electrical current? Electric current is simply the flow of charge. It's a measure of the flow of charge. Whenever we have electrons flowing in a wire, that constitutes a current. It is measured in coulombs per second that we call amperes or simply amps. So essentially it is the amount of charge crossing through a cross-sectional area, like here, per unit time. Remember, the electrons have a charge of minus 1.610 to the minus 19 coulombs. If you do the math, that means a negative 1 coulomb, which is 6 10 to the 18 electrons. Electrons flow in a direction opposite to the current. Implicitly, we are talking of a positive charge flow, even though it is actually electrons that are negative that are flowing. So assume charges are moving perpendicular to a surface, like here in a straight line perpendicular to the surface area A. So what we define as current is delta Q over delta T. Again, 1 amp is 1 coulomb per second. Okay, what we call as current density is the current per unit area. So I over A being the cross-sectional area, is what we call the current density. It has the units, of course, of amps. That's the unit of current per meter squared. What we define as Ohm's law is that the current density is proportional to the electrical field within that conductor. J, the current density, is sigma E. So the current density is equal to sigma times E. That constant of proportionality sigma is what we call the conductivity of the conductor. That's a quantity that depends only on the material of the conductor. In a simplified model for conductors, the conductivity is given by an expression like this: N tau Q squared over N. Now, N would be the number of charges. Tau is a material-dependent characteristic of the conductor, so it's a characteristic of the conductor. Q is the charge of the charges, the electrons in this case, and M is their masses. That would be the conductivity, an expression, a simplified expression of the conductivity. Ohm's law actually states that for many materials, not all materials, many materials, the ratio of the current density to the electrical field is a constant. That's basically what we have from Ohm's law. Most metals, but not all metals, obey Ohm's law. When they do, we call them ohmic. Materials that do not obey Ohm's law, we call them non-ohmic. Ohm's law is not a fundamental law of nature. It is an empirical relationship that's valid only for certain materials. The way you saw Ohm's law in lab was a little different. We are getting to it here. Okay, let's consider a conductor here, subject to a voltage difference delta V. So we have an electrical field within it, E. So the relationship between this constant electric field within the conductor and the electrical potential difference is E times L. Solving for E, that's delta V over L. Remember, L is the length of that portion of the conductor. However, E from Ohm's law is J over the conductivity, with J being the current over the area. Now, if we go back here, delta V is E times L. So this is the L. And then for E, we are going to have J over sigma, but J, we're going to have I over A. So that makes it E I over sigma A. So that's why we have here L, that's the L here, and I over sigma A, that's the electrical field. Now if we separate the I, L over sigma A is what we call resistance. And that's the expression you are familiar with for Ohm's law. Delta V is equal to RI. The voltage applied across the ends of a conductor is proportional to the current through the conductor. And that constant of proportionality is what we call the resistance of the conductor. The SI units of resistor, volts per amps, is what we call the ohm. We use the capital omega for that unit.